Hey everybody, it's Mr. Ray here with our next lesson in grade 12 Calculus and Vectors. We are working in the Introduction to Vectors unit, and today we're going to be looking at expanding our coordinate system from a 2-coordinate system into a 3-coordinate system. So basically 2 dimensions on a flat piece of paper into actual 3-dimensional space. We call these spaces R2 and R3, okay, with a, looks like it's a exponent, R2, R3. And please don't pronounce it R squared or R cubed, it's R2 and R3. So R2 refers to 2 space, or 2 dimensions, and is represented by a 2-coordinate system, typically X and Y. And R3 extends that into 3 space, or 3 dimensions, and we add an extra coordinate, the Z coordinate, to depict that 3 dimensions. Okay, a couple other important definitions here. This is the most important. A position vector is a vector that begins at the origin of either R2 or R3 and connects to the point that you're referring to. So tail is at the origin and the head is at the designated point that you're trying to get to in either R2 or R3. And a plane. Planes don't really exist in R2 because the whole R2 is one plane, like the piece of paper you're writing on. But once you extend into R3, you create all sorts of infinite number of planes. And a plane is a flat 2-dimensional surface that extends infinitely far. For example, I could pick up a piece of cardboard and just rotate it in space, and imagine that that cardboard extends infinitely in all directions. So you basically have a flat 2-dimensional surface, and we call that a plane. Now when we draw planes later on, obviously it's pretty hard to draw a flat surface that extends infinitely far, so we usually depict it as just a rectangular plane, just so you can actually see some edges and understand what's going on there. And the last thing here, right-handed system of coordinates, and this is a method to visualize the location of the axes. We're going to talk about that at the bottom of the page. And obviously you only need this for R3. You've been working in 2-dimensional coordinates X and Y for years and years, so I think you won't have a problem continuing that. Okay, some of the key concepts. In R2 and R3, the location of every point is unique. As a result, every vector drawn with its tail at the origin and the head at a point is also unique. This type of vector is called a position vector, which we have just spoken about. We are going to be using these a lot. So just remember, they always start at the origin, and the head of the vector is at the point that you're targeted, or you're traveling to from the origin. Now in R2, if you have a point, and if you point AB, so A is the X coordinate, B is the Y coordinate, you know that the point is A units from the origin along the X axis and B units parallel to the Y axis. So basically, when you're creating a point in R2, you travel along the X axis till you get to the desired X value or X coordinate, and then once you're there, you either move up or down, in this case B units, to get to the unique point AB. And the position vector OP getting to that point, so from the origin to the point P, has its tail located at O, which has coordinates 0, 0, and its head at point P that has coordinates AB. Now in R3, we just extend that. We now have this third coordinate. This is the Z coordinate. We'll call it C for just a sample coordinate. So again, you kind of do the same process. You just keep going. So point ABC is a point that's A units along the x-axis, starting at the origin. And then once you get to that place along the x-axis where your x coordinate lies, then you go B units parallel to the y-axis till you get to the desired y value, and then finally you move C units parallel to the z-axis. So it sounds more complicated than it is. It's really just extending what we already do with a two-dimensional grid to a three-dimensional grid. And the position vector OP has its tail located at the origin. And again, this time the point P is at coordinates A, B, and C because it's in R3. Now, in R3, the three mutually perpendicular axes, and we'll see this in a second, form a right-handed system. So if we look at this, and I'll try to show it a little bit better, but hopefully you can see, if you were just to draw the flat space and you got what used to be your x-axis here and your y-axis here, well, now the x-axis is going to be called your y-axis. Your formerly y-axis is now the z-axis going up, and now you have this new axis coming out of the paper, and we always draw it like at an angle, because obviously if you have it coming out of the paper, it's just a single point, and that's your z-axis. So what is, you can see a hand behind here, so I'll try to do this demonstration using the document camera. If you put your right hand in front of you, okay, so you've got your thumb pointing out to the right, all your fingers pointing straight up. So if I put down these two fingers, I keep my index finger pointing straight up, and my second finger is pointing basically out of the table or paper. Okay, so this is the right-handed system of coordinates. So each of these fingers slash thumb is a positive axis on our R3 space. So the finger that's pointing out of the paper, your second finger, that's your x-axis, and the thumb that's pointing to the right, that's your positive y-axis, and the index finger that's pointing up is your positive z-axis. So x, y, z. Okay, so another way to remember that is you basically rename your x-axis to the y-axis, you rename the y-axis to the z-axis, and then you have this brand new axis coming out of the paper, and that's your new x-axis. Okay, and those are all the positive ends. So positive is coming out of the paper at the front. The negative x-axis would be going out the back, and then your y-axis is going to the right. Positive y-axis is going to the right. Negative y-axis going to the left. Positive z-axis is going up, and negative z-axis is going down. Okay, so that's how we're going to talk about our coordinate system in R3. Okay, so let me zoom back to a regular level here. So position vectors, we've talked about this a few times now. So in R2, let's talk about position vector. So position vectors in R2 always has its tail at 0, 0, which is the origin. And if I have a point P here, and I draw a vector from O to P with a head there, and there's my point P, and say I gave it coordinates A, B. So on the y-axis that would be value of B, and on the x-axis that has a value of A. That is my position vector OP. Now, one thing I want to note here, I'll try to mention it several times. When I mention vectors and components of vectors, for example, I'm talking about the position vector OP, and I've got my A and B in square brackets. Okay, I like to do this to show that if you just see this, you know that's a vector. Those are vector components, and it's not a point AB. Okay, if it's got round brackets like this or this, those are actually coordinates in R2, not a vector in R2. That would be a vector in R2. Okay, and the textbook unfortunately uses round brackets for both, and it can get a little confusing, but for my notes and the way I do the homework solutions, I always use square brackets for vector components, round brackets for coordinates. Okay, so that's the difference there. If we move to R3, talk about a position vector in R3. This time the tail still at the origin, but this time the origin is the point 0, 0, 0 because you've got x, y, and z coordinates. So that's located right at the intersection of all three axes, and we display this vector going from 0, 0, 0 to ABC as a position vector. Now this is where it gets a little complicated. I can't just, unlike R2 where I could just put a point and you could definitely tell me the coordinates of that point because the paper is art in 2 space. If I just put a point on the grid here, it could actually represent an infinite number of possible points. So the way we actually graph them, and I'll try to keep this to a minimum requirement, but if I had, for example, if you look at this as an example, you can see I'm going to go x units out to that point there. Okay, and so that's going to represent my x coordinate. When I want to draw my y coordinate, what I do is I draw a line parallel to the y-axis that many units. So, for example, if that's the value of my y, I go that many units. Now, what I'm comparing this to is, the length along here from 0 to my y coordinate along the y-axis is going to be the same length over here. So I'm basically drawing like a parallelogram. So I draw the line out there to my x coordinate, then a line parallel to my y axis, that y units. I get to my second point, and right now I just have my x and y coordinate, and then I actually go up or down z units. So it's like you're creating like a box. So I go up to there, and then I've got my point x, y, z. I draw on the grid, and then my position vector goes from the origin to that point. So that would be my vector OP. Okay, and you can sort of see the same thing here. This is just showing the positive and negative x, y, z axis. But I don't want to do it on here. I think this is a much better way of seeing it. And we'll do some more examples of drawing points in 3 space or R3. Okay, I've got this exercise now to kind of introduce you into 3 space. And what this is, it's the diagram below here is a 2-dimensional representation of a 3-dimensional classroom. Okay, obviously it's not going to be 3-dimensional representation because it's on a piece of paper. And so you can see the classroom here. Here's the floor. We've got the left wall over here, the front wall there, desks on the floor, got things on the wall. And it's given us some measurements here. It says that the length is 10 meters, so that's the left wall. Okay, so the left wall is 10 meters long. Now the way we've done these little boxes here, that's a grid system. So if I counted along here, I'd see there'd be 10 units long. Similarly, the front wall is 8. And the height of the classroom, you can see just by counting, 1, 2, 3, 4, the height is 4 meters, which you can also see over here. So, in terms of how we're representing, you can see I've labeled the x-axis, the y-axis, and the z-axis, and these correspond to the way we would do it on a graph in R3. So the z-axis is kind of coming out of the paper, y-axis, positive y-axis going to the right, positive z-axis going up. So basically any point in the classroom I could represent through an XYZ coordinate. Okay, so there's a whole series of questions here that are going to help us maybe get a better understanding of how this works. So we need 3 coordinate axes to describe the position of points in 3 space. I just sort of mentioned this. So which axis runs along the intersection of the floor and the left wall? So there's the floor meeting the left wall. That would be the x-axis. Okay. Which axis runs along the intersection of the floor and the front wall? So that would be along that edge there. That's the y-axis. And you probably guess what the next one is. Which axis runs along the intersection of the front wall and the left? So where these 2 walls meet, that would be the z-axis. What point does the front left corner of the floor of the classroom represent? So that would be where all 3 axes meet, and that would be the point 0, 0, 0. So that's the origin of this classroom, and that was just a decision that's made based on where we draw the grid. Okay, so that's the point. And notice I'm using I'll be using brown brackets to represent points. Let me move that up. Okay, what angle do the 3 axes make with each other? You can definitely see the z and the y-axis. They make a 90 degree. A little harder to see with the z-axis, but based on the angles that I'm drawing, you can also see that these should be 90 degrees also. So all of the angles of the axes meeting are 90 degrees. Okay, so we might want this around. Let's keep this handy. So if we continue on with this questioning, the 3 coordinate axes taken in pairs determine 3 planes called coordinate planes. So a plane is made up of, well, in this case, 2 axes. Okay, so for example, the xy plane is the plane that contains the x and y axes. So, and then we can answer these questions. Hopefully that will help our understanding. Which plane do each of these represent? So the floor, you can see the floor on the bottom here. So which axes make up that plane? Well, that would be the x-axis over here and the y-axis over here. Between the 2 of them, it's defining the floor. So that would be the xy plane is the floor. The front wall, so the front wall, obviously, let me move this down a little bit. Front wall's over here. That's made up of the z-axis and the y-axis, so that would be the YZ plane. We always put it alphabetically. And then the left wall, so the left wall is made up of the x-axis and the z-axis. So that would be the XZ plane. Okay, what are the equations of each of the planes in question 2? Okay, this is a little bit more difficult. So what we mean by equations is what equation represents every point on each of these planes. Now, so for the XY plane, the floor, I mean the X values and the Y values are changing, but what's going on with the Z coordinate? The Z coordinate for all of the points on the floor is Z equals 0, and that happens to be the equation of the floor, or the XY plane, whatever way you want to describe it. So you can see the relationship here. If I'm talking about the XY plane, the equation is z equals 0. So it's the coordinate that's not mentioned in the plane. So z equals 0. Similarly, the front wall, the YZ plane, the y and the z coordinates are constantly changing, but the x coordinate is not changing. The x coordinate for every point on the wall is x equals 0. And that lines up with what we learned on the previous one. The YZ plane, the only coordinate that's not changing is x. It's always 0. So, and you can probably guess the next one, the left wall, the XZ plane. The only coordinate that's not changing is the y coordinate. So the y coordinate for every point on the left wall is y equals 0. So that is actually the equation of those walls or floors or planes. Okay, the next part. The three coordinate planes divide 3 space into 8 regions called octants. So if you recall, thinking back to 2 space, where we just had x and y coordinates, we actually had quadrants because there's 4 of them. So we had 4 quadrants in 2 space. We have 8 octants in 3 space. Okay. The octant where x, y, and z are all positive is called the first octant. On the diagram, visualize the negative x, y, and z axes and imagine 7 other rooms situated in the 7 octants. So basically this classroom is just one octant. It's the octant where x, y, and z are all positive. Okay, now you could imagine, if you extend these axes, well, extend the z down, extend the y to the left, and the x through the back. Okay, you're now creating another 7 rooms or 7 regions, seven of the octants. So let's kind of go through this exercise here. It kind of helps understand it a bit better. On the diagram, visualize the negative x, y, and z axes. We just did that. Imagine the other 7 rooms in the 7 octants. How many of these rooms are located on the same floor as the classroom? Describe the location of each room and state the sign of x, y, z in that room. So if it's on the same floor, you can imagine if you walk out this door to the left, well, there's another room. If you could go through this wall where the blackboard is, there's another room back here, and then there's a third room kind of beside, well, it only meets this room at this corner here. It's kind of beside this room and beside the back room here. So let's go through. So for the 4 rooms, so if we talk about this room here, the classroom we're looking at, this would be considered the top front right room. Okay, and it's x, y, and z coordinates, as we've already talked about. This would have a positive x, positive y, positive z. So I'll just put 3 pluses. Okay, and if my next room was top front left, well, that's the room through the door here. So what coordinate is changing its sign here? Well, that would be the y coordinate, because now y is moving into the negative y, whereas x and z are still positive. So in this case, let's call it the top front left. So that's the room to the left of our classroom. So x and z are both positive still. Y is now negative. Okay, and if our next room was, we call it the top back right, so the room that's through this wall here. So what's changing in this situation? Well, now the x coordinate, we're going to the negative x values behind here, but the y and z values are still positive. So we can call that room top, back, right. So again, we said the negative. The x coordinate is negative, but the other two coordinates are positive. And then the last room that's kind of back in here, let's call that the top, back, left. Sorry about that, top, back, left. Okay, now let's imagine these coordinates. So let's see the x coordinate. So the x coordinate, since it's back over here, x would be negative, and also y would be negative because it's to the left of this room on this side. But the z coordinate, it's still on the same floor. So we would have negative x, negative y, positive z. Oops. Now, what do these all have in common? Well, if you notice, the only thing they have in common in terms of the sign is the positive z coordinate. And that's because these rooms that we just talked about are all on the same floor. So the vertical coordinate is always positive. Okay. The other thing they have in common in the description is top. So this is on the top floor, and that means the z coordinate is always going to be positive. Okay, so there's 4 rooms on the same floor as the classroom, including the classroom. The next question, how many rooms are located on a different floor than the classroom? Well, if you look at our picture, well, this is the top floor, so there's nothing above here. But for each of the rooms we just talked about, there is now going to be a room right below the 4 rooms we just talked about. So that means there's another 4 rooms on the floor below. So we're going to describe each room again. So I'm just going to use reference to the ones that we already mentioned and then talk about the room that is directly below. So instead of top, we're going to be saying bottom. So bottom, front, right. So that's the room directly below our classroom. So in terms of x and y, they're still both positive. So it's still at the front, it's still at the right. So x and y are positive, but now it's a floor below. So the the z coordinate is going to change to negative. And that's really what happens to all these rooms. We just flip the z coordinate to negative. So positive, positive, negative. Okay, then the top, front, left. So if we talk about the room that's directly below the room that's behind this left wall, well, let's compare it to, instead of top, front, left, it's now bottom, front, left. Okay, and it had positive x, that's still the same. A negative y, that's still the same because now it's, it's now to the left. So positive, negative, and now the z coordinate has changed from positive to negative because it's on the bottom floor, or the floor below. Our next room would be, instead of top, back, right, we've got bottom, back, right. Okay, and that room, so bottom, so that would be the room that's directly below the room that's back behind the front wall here. So it's still on the right side, it's at the back, and it's at the bottom. So so that would, the x and y coordinates remain at negative, positive, but now the z coordinate becomes negative because it's a floor below. Okay, and finally we've got the bottom, back, left. So this is probably the most difficult room to imagine. If we stay on this floor, we go over to this side and then back, and then 1 floor below. So basically everything is negative. We're on the we're on the back part, so x is negative. We're on the left part, so y is negative. And we're on the floor below, so z is negative. So all three of these coordinates in that room will be negative. Okay, which corner point do all 8 rooms have in common? Well, that would be the origin, where all the axes meet. So 0, 0, 0. And points in 3 space are represented by an ordered triple of real numbers. To locate the point x, y, z, start at the origin. And again, this is what we've looked at before. Move x units along the x-axis, then y units parallel to the y-axis, and then z units parallel to the z-axis. Determine the coordinates of each point as accurately as you can. So the 8 corners of the classroom Okay, so if I start at the origin, so you can see where the 8 corners are on the floor. We've got, let me make this so you can see it all. On the floor, we've got 1, 2, 3, 4 corners, and then on the ceiling we have 4 more corners. 1, 2, 3, 4. So we're just being asked to put all the 8 corner coordinates. So of course, we can start with that corner, which is the origin. So we've got 0, 0, 0 is our first point. Okay, if I move down to this corner, you can see, well, the x coordinate has now changed from 0 to 10. So that would be 10, 0, 0. If I went along this to the floor corner over here, that has a y coordinate of 8. X and z are still 0, so that would be 0, 8, 0. And then finally, this corner here, well, this is going to have an x coordinate of 10 because we're 10 away from that wall, and also a y coordinate of 8. So that would be 10, 8, 0. Okay, you notice they all have a 0 for the z coordinate. That's because these are all 4 of these are on the floor. Okay, but now if we move up to the ceiling, we're going to have basically the same 4 points, but now the z value is changing from 0 to the height of the wall, which is 4 meters. So the z coordinate is going to change to 4. So if I compare, if I look at the 0, 0, 0, the corner that's directly above there on the ceiling would be 0, 0, 4. The front left corner, that's the point on the floor. The point on the ceiling above that would be 10, 0, 4. If I move up to the top corner of that, 0, 8, 4 would be the corner in the ceiling above that point. And finally, in the very, very front at the top of the ceiling, this would have all x, y, and z have an actual value. So the x coordinate would be 10, the y coordinate would be 8, and the z coordinate would be 4. So 10, 8, 4. Okay, so we've got all 8 corners of the room. Now we're going to actually, this is a good exercise, we're going to try to find the coordinates of a very unique point in the classroom. Okay, so if I went back to my picture here, the first thing we want to find is the center of the classroom clock. So the classroom clock is over here. So in terms of, so it's right on that wall. So I'll assume it's part of the wall for this exercise. So if I'm looking at the x coordinate, how far is it from the back wall? Well, I'm going to use this grid to help me. So it's basically has that x value there, which if I count here it'd be 1, 2, 3, 4, 5. So the x coordinate for the clock will be, what did I just say, 5. The y coordinate, so that's the distance from this left wall, well, it's right in the left wall. It's not, so that would be 0 because it's right along this plane here that represents the left wall. So x coordinate of 5, y coordinate of 0, and then the z coordinate is how high up it is. So again, I'm going to use the grid to help me. So it's that point right there, so that'd be 1, 2, 3. So it'd be the point 5, 5, 0, 3. So if I go back to my lesson note here, point 503 represents the center of the clock. The next one is the top left corner of the blackboard. So that would be this point right here. Okay, so how can I put that point in terms of its coordinates? So always start with x. So this time x, how far is it from the front wall? Well, it's on the front wall. So in this case, the x coordinate is 0. The y coordinate would be the distance from the left wall because it's along this y-axis. So that would be, looks like it's between 1 and 2. So I'm going to say 1.5. And then the height. So the height of that point, if I count down from the bottom, 1, 2, 2.5. So that coordinate would be 0 for x, 1.5 for y, 2.5 for z. So 0, 1.5, 2.5. Okay, the last one is the top of the teacher's head. This is by far the most difficult one because it's not along one of the walls or floors. And it's a little hard to see with the grid's a little more complicated here. So the teacher, well, there's the teacher. The top of her head is right there. So I have to kind of imagine if I dropped a vertical point. So it's kind of down here. A little hard to see, I agree. But on the floor, the teacher's location is right about there. So if I was doing the x and y coordinate, I could see that, well, x is how far it is from the back wall. It looks like it's 2 units in the positive x direction. Okay, in terms of y, if I'm counting, this is a little more difficult. So that comes back to here on the front wall. So that would be 1, 2, 3, 4. So it's 2, 4 so far. And the top of her head, this is definitely the most difficult part. For one reason, she's sitting down. But if I was to measure, if I was to draw a line from here to here, okay, and then compare that to the grid, probably looks like it's about 1.5 meters, that the height of that line. So I'm guessing, fairly accurate guess, I would say, would be 1.5 meters for the z coordinate. And remember, we had 2 for x, 4 for y, 1.5 for z. So that was by far the most difficult coordinate to find, just because it wasn't along a wall or a floor or the ceiling. Okay. So last page here, a few more questions to do. What are the y and z coordinates of every point on the x-axis? So if we look at our classroom again, so the x-axis is along here. Okay, so you can see as I move along the x-axis, the x coordinate is changing. What's happening to the y and the z coordinates? Well, they're 0. Okay, in terms of left-right position, stays at 0 the whole time. In terms of a vertical position, stays at 0. So the answer to the question is the x and y coordinates are along the x-axis are always 0. And then we look at the same thing for the y-axis. What are the x and z coordinates? So same idea here. So the y coordinate is changing as I move along, but the x coordinate is always 0. And the z coordinate is always 0. So those are also 0. And you can probably guess the next one. What are the x and y coordinates of every point on the z-axis? So as I move along the z-axis, you'd agree that my front to back coordinate not changing, so x is not changing, it's 0, and the left to right coordinate, the y coordinate, is also not changing, so again 0 for the x and y coordinates. What is the z coordinate of every point on the xy plane? So again, if I look at my xy plane, that's basically the floor. We already talked about that. What's the z coordinate of every point on the floor? That would also be 0. What's the y coordinate every point on the xz plane? So the xz plane is the left wall. And what's the y coordinate of every point there? 0. And this will be no surprise. What's the x coordinate of every point on the yz plane? So the yz plane is the back wall or front wall. So what's happening to the x coordinate there? Well, nothing, because every point along there has an x coordinate of 0. So lots of zeros in a row here. Now, here's where we actually come up with the condition, which gives us the equation of these planes. So the back wall is the wall we can see through here. Now, in terms of the coordinates here, what is actually staying the same? Well, the x and the z are changing all the time. The y and the z are changing all the time as we go left, right, and up and down. But the x position, how far are we from the front wall? That's always going to be 10. So the equation of the back wall is x equals 10. That defines every point along here. Okay, what about the ceiling? Well, what's changing with the ceiling? Well, the x and y are constantly changing as we move around the ceiling, but what's staying the same is the z coordinate is always the same, and that is 4, because that's the height of the ceiling. And then the right wall, which is over here, you can see that, well, the x coordinate and the z coordinate are changing, but the y coordinate is always z equals 8. Sorry, y equals 8. Okay, so that's how you kind of think in terms of equations of a plane. You talk about, well, which coordinate is not changing, and if it's not changing, what's its value? Okay, so I agree this was a fairly long lesson, but it's a kind of a complex topic, getting to know points in 3 space. How do you define them? How do you relate them to planes? How do you relate them to their axes? So I've got some homework assigned here, hopefully help you with practicing coordinates in 3 space and a little bit in 2 space as well. So hope that helps you understand life in 3 space, and we'll continue on. The next lesson we're going to be talking about working with vectors in 2 space and 3 space. Until we see you next time, have a great day.